So for this problem, we will moving to the motion in the part that we already know. And you see that for this type of problem, you see that it's maybe more convenient to solve the motion, to derive the motion in polar coordinate system instead of x and y coordinate. And also it's maybe more convenient than normal and tangential coordinate system. Because of what? Because we already know the part. The part is represented in polar coordinate. Okay, the part that we define, the part is already defined in polar coordinate. So then it's maybe more convenient. It's very straightforward to derive the kinematics in terms of polar coordinate system instead of another type. Okay, and for this case, you see that we have the part equation that is in terms of r square equal to 4 cosine 2 theta. Okay, meter square. Okay, this is the unit. It is not the formula. Sorry. Okay, this the formula. It should be just like this. Okay, meter square is a unit, and is the problem gives us that the angular velocity is a function of time, theta dot. Actually, this is omega. Is it a function of time? Is equal to 4t power 3 over 2. Okay, it's function of time. And we would like to determine the velocity and acceleration, magnitude of velocity and acceleration of the particle P, back P, at theta equal to 30 degree. Okay, and for the initial condition, when time equal to 0, theta is equal to 0. So then it means that when time equal to 0, theta equal to 0. So then it's starting here. Okay, and for this case, we use the formula in theta direction. So then from the formula, you will see that we have to working out for the derivative in R and in we have to take the first derivative of R function and theta function with respect to time for the first derivative and second derivative. And after that, we just substitute it into the formula. We obtain the velocity components and acceleration components. So for this case, we can solve like this. Okay, so you see that we starting with take the first derivative to r function and theta function. Because we already know the formula that is over here. Okay, and we already know the r function. Okay, r function is the square. This is in the square term. Okay, actually you may change it to be r equal to square root of 4 cosine 2 theta also, but it may be more convenient to direct take derivative both sides, and you may find this on the left hand side. You may use the chain rule like this, and on the right hand side you use the chain rule, and we have this, and after that we derive for r dot. That's become like this. Okay, in the same manner for r dot dot. Okay, we take the first derivative to the function also. Okay, that you may use this formula to take the second derivative. All right, but it's up to you. It's mathematics. But for this case, I use this one. Okay, and take the first derivative both sides, and you will see that this is just for this type of problem. It's maybe a lot of mathematics in terms of the derivative. Okay, so the mathematics calculus is come back to this type of problem that you may have to practice on that. And after we complete with some manipulation in mathematics term, we obtain r dot dot. In the same manner for theta, we have theta dot equal to this. Okay. So theta dot dot, we take the first derivative and we obtain this function, right? Okay. And for this case, we would like to know when theta equal to 30 degree, that is equal to pi over 6 radian. Okay. Theta is the time is equal to what? Okay. So we have to integrate the omega that we already know. We have the theta dot equal to this. And after we integrate it, we have this function and we apply for the initial condition. We found out c should be 0 and we obtain the theta function instead of theta dot function. Okay, when we have this and we substitute for theta equal to 30 degree, but for the formula that we have, we cannot substitute in degree into the formula. One thing that you have, I would like you to remember that for normally in the formula in mechanics and in physics, if we follow the angle formula is always used in radian. Okay, it's always used in radian. We will use angle to be degree just only in case that we use it with trigonometry function only. Okay, that we can use degree. But for another cases that we solve for angle, we normally use it in radian. Okay, do not use the angle in degree in the formula. Okay. So for this case, we change 30 degree to be radian, and then we found out the time for 30 degree, it should be 0.6397 seconds. That is we use for determine the theta dot dot, that's angular acceleration. And after that, we use the same value, substitute it for r dot dot at theta equal to 30 degree, we obtain here. Okay, so after that, we substitute back into the formula to determine for each component. Okay, for VR, we obtain VR equal to minus 5.014. Minus 5.014. What does it mean? It means that the velocity in R direction is opposite to the R direction, right? R is go out. Okay, but for this case, VR is go inside. Okay, instead. Okay, for R theta, it has two components. Velocity, it has two components. We have V theta. V theta is equal to R theta dot. And we have the magnitude of 2.895. And we can represent for velocity vector, it's become here. And for the magnitude, is over here. For acceleration, we have two components also. We have AR. We use this formula. We substitute. We obtain this. And AR is its negative value. Okay. It is negative value. So that means that it's go in the normal direction, right? It's go inside. It's opposite to R direction. Okay. And for A theta, it's negative also. So after that, when we substitute it's inside of this, we obtain the acceleration, the magnitude of acceleration for this case. Okay. So for this problem, a lot of mathematics manipulation. I recommend you to review this problem again. Take time and try to take the first derivative and second derivative by yourself by trying to do it by yourself. Okay. And for this case, after we finish it, I will show you some picture. The I hope that this picture maybe make you more understanding. Okay, you see that I try to draw the particle uh, in any point along the path. Okay, you see that at the starting point. Okay, R and normal is maybe very close to the same direction. Okay, and tangential direction and theta direction is maybe matched to the same direction. Actually, it's maybe not the same directly. Okay, but at the starting point, it's maybe very close. Okay, and after that, when it's moving in a few minutes, okay, it's changed to another position. It's changed to another position. It's maybe moving here. Okay, it's maybe moving around here. From this point, it's maybe R and N. It's maybe matched to each other, but R is go out from the center of curve, but N is normally is go to the center of curve. Okay, R is go out from the original O. Okay, N is go inside to the center of curve. When it's moving to this point, okay, you see that R is always go out from the reference O, reference point O. But N is always toward to the center of curve. That is this curve on this point of curve. So the center of curve is maybe around here. So then normal is change. It should be this direction. And it means that tangential direction should be changed. And you see, tangential direction and theta is not the same. Okay? So for this case, you will see that when you derive the velocity in r theta, you will have VR and V theta. And after you combine together, it becomes just only one. That is in tangential direction. Okay, but you see that for this case, it's not convenient to solve in x and in y, right? Because the function is represented in r and in theta. Okay, if you solve in x and in y, actually you can do, but you have to change the part function in x and in y direction. That is maybe not convenient. Okay, and in normal and tangential also, because for this case you don't know anything for the velocity magnitude and acceleration magnitude. Okay, you just know just only the part function that is not in normal and tangential direction. It is in r and in theta coordinate. So then it is not convenient also to solve it directly in normal and in tangential direction at first. Okay, so it's more convenient to solve in r and in theta instead for this type of problem. Okay, and I hope that these pictures may be helpful for you to understand more for r theta coordinate and normal and tangential, and also Cartesian coordinate system. Let's complete this problem.